We saw in the previous video that the Laplace transform of the first derivative of f of t is s times f of s minus f of 0. I now want to consider the Laplace transform of f double prime of t. By definition, it's the integral from 0 to infinity of e to the negative st times f double prime of t dt. As we did in the previous video, I'm going to use integration by parts, and u is e to the negative st, so that du is negative se to the negative st dt. dv is f double prime of t dt, so that v is f prime of t. The integration by parts formula gives us that this is f prime of t divided by e to the st evaluated from 0 to infinity, plus s times the integral from 0 to infinity of e to the negative st times f prime of t dt. If f prime of t is of exponential order, then the limit as t goes to infinity is going to be 0 for that expression. Plugging in 0 in place of t is going to give us negative f prime of 0. And then for the next term, we have this integral. That integral is exactly the Laplace transform of f prime of t. And so it can be replaced. We have s times f of s minus f of 0. This gives us a formula that we can generalize. If f, its derivative, and all the way to its n minus first derivatives are continuous on the interval from 0 to infinity and of exponential order, and if f, well, the nth derivative of f is piecewise continuous on that interval from 0 to infinity, then the Laplace transform of the nth derivative of f has the form s to the n times f of s minus s to the n minus 1 times lowercase f of 0 all the way down to minus the n minus first derivative of lowercase f at 0. So the formula tells us if, for instance, we have a third derivative of f here, then the first term on the Laplace transform side would be s cubed. Then we would have an s squared and an s to the first power all the way to having no s at all. The first term will have an uppercase f of s. All the rest of them will be lowercase f, f prime, and in this case it would be up to f double prime, evaluated at 0. And then this bit here where uppercase f of s is the Laplace transform, that's just connecting the uppercase f to the lowercase f. Rather than talking about this more, let's see an example. We're going to solve the initial value problem. Y double prime minus 4y prime equals 6e to the 3t minus 3e to the negative t, where y of 0 is equal to 1 and y prime of 0 is equal to negative 1. We'll need the Laplace transform of y double prime and the Laplace transform of y prime. The Laplace transform of y double prime, according to the formula we just saw, is s squared times y of s minus s times y of 0 minus y prime of 0. For minus 4y prime, we have negative 4 times the Laplace transform of y prime, which is s y of s minus y of 0, equals 6 times the Laplace transform of e to the 3t. So that's going to be 6 over s minus 3 minus 3 times the Laplace transform of e to the negative t. So that's going to be minus 3 over s plus 1. Y of 0 is equal to 1, so we're going to substitute 1 wherever we see y of 0. And y prime of 0 is negative 1, so we'll likewise substitute for that. The result is s squared times y of s minus s plus 1 minus 4s y of s plus 4 is equal to 6 over s minus 3 minus 3 over s plus 1. Don't forget to distribute the negative 4. That's a common thing to do. Another thing is not remembering that after the initial s squared times y of s, or the s times y of s, all the other terms in the transform of a derivative have a minus sign in front of them. So make sure you keep track of all those minuses. and the coefficients. We want to solve for y of s, so we're going to gather those terms together and factor. We have s squared minus 4s times y of s. And then we want everything that doesn't have that uppercase y of s on the other side. So we have 6 over s minus 3 over s minus 1 plus s minus 5. I'm going to skip some algebraic steps here, but I'll tell you what's going to happen here. We've got two fractions and then two other terms on the right-hand side. And the way to go here, folks, is we're going to end up dividing by s squared minus 4s. And folks, we need to get common denominators on the right-hand side first. So you can verify on your own that once we get common denominators on the right-hand side and divide by s squared minus 4s to isolate y of s, that we end up with y of s is equal to s cubed minus 7s squared plus 10s plus 30, all divided by s times s minus 4 times s minus 3 times s plus 1. The partial fraction decomposition for that function is s cubed minus 7s squared plus 10s plus 30 over that denominator, s times s minus 4, s minus 3 times s plus 1 equals four fractions, one with the denominator of s, one with the denominator of s minus 4, another with the denominator of s minus 3, and another with the denominator of s plus 1. Those denominators are all linear, and so our numerators are a, b, c, and d respectively. I want to step back for a moment, though. The reason we're able to perform partial fraction decomposition is that we have a proper fraction up here, proper rational expression. The degree of the numerator is less than the degree of the denominator. That's in keeping with a theorem that we saw before. This thing does go to 0 as s approaches infinity. If we have an expression on the right-hand side after solving for y that doesn't go to 0, then I'd say go back and look for a mistake. We saw a theorem that tells us we expect this to happen. Now remember that this partial fraction decomposition represents uppercase y of s. And you've seen how I roll with something like this, just zeroing out various factors to isolate our coefficients here. I'll skip the details, you can verify them on your own. We end up with y of s is equal to 5 halves over s plus 11 tenths over s minus 4 plus 2 over s minus 3 minus 3/5 over s plus 1. Applying the inverse transform gives us the solution of y of t equals 5 halves plus 11 over 10 e to the 4t plus 2e to the 3t minus 3/5 e to the negative t.